So let's consider the function f of xy is x squared plus 2xy. So the partials of this are 2x plus 2y with respect to x, and fy is 2x. So if we want to set these equal to 0 for the first derivative test, so in order for fx to be 0, we would need x to be equal to negative y. For this to be 0, and for fy to be 0, we would need x is equal to 0. So the only critical point is when x is equal to 0 and y is equal to negative x, so at the origin. But this is not a local max or a local min. We can see that, I guess from the picture, we can see that from looking at this the equation for f. So f of 0, 0 is 0. If we fix y, then f of x0 is equal to x squared, so it'll be greater than equal to 0 as we travel along in the x direction. But if we fix x small and y less than equal to 0, so this will be x times x plus 2y. So if we pick x to be greater than 0, but y such that such that this is less than 0, then this will be less than 0. So this implies that like f of 0, 0 is not a local max, because there's things that are larger than it nearby the origin, and this tells us it's not a local min. So the origin is what we call a saddle point for this function. So we can also see this using, so here this was sort of a direct way of seeing this using the Hessian, sort of the systematic way of doing this. So the Hessian, first let's rewrite. So fx is 2x plus 2y, fy is 2x, and so then the second derivatives will be fxx is 2, fxy is 2, and fyy is 0. So the Hessian of f be the determinant of 2, 0, 2, 2, which is negative 4. And so since the Hessian is negative, this is how we can conclude that the origin is a saddle point.